This video is on inverse functions, which is the second part of section 5.2. As always, you'll need to take notes on the examples and the note slides that I have in the video. First, I'm going to explain what an inverse is, and then I'm going to go through a couple examples of how you can find inverses and when inverses exist. To start, we should look at the notation. This is the notation implying that you have an inverse function. You read this as f inverse of x. So it's not f to the negative 1 of x. You would read this as f inverse of x. So an inverse function kind of undoes what you did with the original function. For example, if I have f of a and that equals b, that means that I put in an a value into my function and my output, my answer, my y value, turned out to be b. An inverse function says that if you put that same b value into your inverse function, you will get out your original. So you will have gone backwards, basically. Another way that this is often explained is by just using some mapping from the domain to the range. So that's not written very well, but here's my domain and here's my range. So for example, my domain values, I'm just choosing some x values here, could be negative 1, 2, 3, and then if I say my function, so my f of x is, 2x minus 5, then if I put negative 1 into this function, I would get 2 times negative 1 minus 5, which would be negative 2 minus 5, which is negative 7. So my domain value would map to a range value of negative 7. And if I were to put in 2, the same thing would happen in 3. So I'll do one more. If I were to put in 3, that would be 2 times 3 minus 5, which would be 1. So my point when my x value is 3, that would map to 1. So in inverse function, what happens there is that I'm starting with 1, and I'm going to do some new function that when I put 1 into the function, I will get 3 back. So I will have essentially undone what I did with this function. So in this function, I inputted 3 and it outputted 1. And the inverse function for this, I would put in 1 and I would output 3. So it would take me back to where I started. Let's look at some examples. Actually, before we look at some examples, I wanted to give you the notes for how you will find the inverse of a function if you're given a function and if you're given a graph. Okay, so we will attack these problems differently. So if you're given a function, some equation, then what you would do is you would switch the x and y values, which I know sounds very strange, and then you would resolve the function for y. Once you resolved it for y, though, you do want to then use your inverse notation. So you would replace the y with f inverse of x. Again, I am going to do some examples of both when we have a function and when we have a graph. So in a function, again, you will switch x and y and resolve for y. Please make sure you have this in your notes. If you're just given a graph, so you're given a picture of your function, then to graph the inverse function, you would actually reflect it over the line y equals x. Or you could, if you make a table of values, you could switch the x and y coordinates and graph those. So we'll look at some examples for each of these scenarios. So in my first example, I'm given an equation. And so on the previous slide, I said that if you're given an equation or a function, the first step will be to switch the x and y values. Now I know this is going to seem very strange, but I'm actually going to write x equals 2y minus 5. Okay, so again, these two equations are not equivalent. I'm finding the inverse function. Once you switch x and y, the next thing you want to do is solve for y, which we've practiced in the last chapter. So I want to isolate y. To isolate y, I would add 5 to both sides. And I like to have the y on the left-hand side, so I'm going to flip the equation. And so it's 2y equals x plus 5. And then divide both sides by 2, and we get y equals x plus 5 over 2. Remember, once you are finished, which we are, we've isolated y, we want to replace the y with our inverse notation. So the inverse is actually f inverse of x is x plus 5 over 2. So we have found the inverse function. Now, this was the example that I used to show you the mapping from domain to range. And if you remember, when I inputted -1 into this original function up here, I got back -7, so that was my output value. And I told you that if you use the inverse function, if you input -7, you will get -1. So I just want to show you that. So if I use my inverse function and I input -7 into my equation, which is down here in the bottom, so -7 plus 5 over 2, that would give me -2 over 2, which is -1. So you'll see that I took my original output value, I input it into the original, and I got back my original input value. So I did, in essence, undo what I had done in the original function. Okay, example 2, find the inverse function for this cubic. Again, I've been given an equation, so I want to solve it by switching the x and y values. Remember, this is just function notation for y. So I'm going to say that x equals y minus 2, all cubed, plus 5. And now I have to isolate y. To do that, the first thing I need to get rid of is the plus 5, so I'm going to subtract 5. And just like I did in the last equation, I'm going to flip the equation. So I'm going to put the y value on the left-hand side. And so we have y minus 2 all cubed equals x minus 5. And from here, I'm not going to distribute that exponent. I do, however, want to get rid of these parentheses. So I need to get rid of this cubed sign, or symbol. And so I'm going to take the cube root of both sides. So I now have the cube root of y minus 2 cubed, which those will just cancel out. And so on the left-hand side, I'll be left with y minus 2, so we're getting closer. Since it's a cube root, I don't need to add in plus or minus. You only need to do that if you're taking an even root. So I just end up with y minus 2 equals the cube root of x minus 5. The last thing I need to do is add 2 to both sides. And so you can have y equals either 2 plus the cube root of x minus 5, or you could put the plus 2 at the end. Just make sure, if you're going to do it that way, that it doesn't look like that 2 is part of the cube root. So there's my cube root, and then it's plus 2. That might have been a little large for a gap, but you understand. It can't look like the 2 is underneath the cube root. So this is my inverse function, but the final thing I want to do is to write my inverse notation. So we have the cube root of x plus 5, then plus 2. So there's my inverse function. Our third example is going to involve graphing inverses, and I'm going to use the same equation that I just found the inverse function for in the last example. So the first thing we need to do is graph this function, and since we haven't really studied how to graph a cubic, we'll need to make a table of values. So I will do that on this slide, and then I will graph them on the next slide. So in my table of values, I just need to choose some random x values. So it's a good idea to choose some negatives. So I'm going to choose -1 and 0, 1 and 2. And maybe that'll be enough for me to see what I have for my graph. Okay, so I'm just going to fill these in. I'll show you the first one and then I'm going to fill the rest of them in. So if I want to find f of -1, then it would be -1 minus 2 all cubed plus 5. That's -3 cubed, which is -27, plus 5. So my final answer is -22, which might be annoying to graph. Maybe I'll choose some more points. Okay, I'm going to fill in the rest of the table. There's the rest of the table filled in. You might want to add another value on there, maybe when x is 3, find the corresponding y value. I am going to graph this on the next slide, but beforehand you will want to write down what I've written here because these are the steps for graphing an inverse. So here is my graph. It is not my best work, and I've included the table over on the left-hand side. I took off -122 because my scale doesn't go down that far, and I didn't want to adjust the scale from being ones. So now that we have our original graphed, the way to get the inverse, I told you, was to, just like we did with the equation, to switch the x and y values. So this is my table for my original, and you should label it as such. Okay, and I'm actually going to switch my pen color here, so everything else is going to be for the inverse. So my inverse table is going to have the x and y values switched. So instead of the point 0, -3, I'm going to have the point -3, 0. I have literally flip-flopped the x and the y value. Instead of 1, 4, I have 4, 1. Instead of 2, 5, 5, 2, and finally 6, 3. All I did was take my original table and flip the x and y values. And then you can graph those. So now I have to graph those points. I'll do that and come back. Okay, so I've graphed my inverse function. So it's really hard to graph on the iPad, by the way, in case you're laughing at my graphs. So this is f inverse of x, and my original was here. Okay, and so I've graphed the inverse. But one more thing that I want to show you is that, which I think I put on the previous slide, that a graph and its inverse are actually reflections of one another. Maybe you can see that if you can tilt your screen if you're on an iPad. You might see that they are actually reflected over a diagonal line, and that diagonal line is a special line. It's the line y equals x. The line y equals x is special because it's where x and y are equal. And hopefully you're noticing that that's exactly what we've said here. I've taken the x values from my original and I've made them the y value. So I've said it's what y equals. And I've taken my y value and I've said it's what x equals. So it's where x and y are equal. I'm going to draw that line in now. So you'll notice the line goes through 1, 1, 2, 2, 3, 3, 4, 4, -1, -1. It's where the x and y values would be equal, hence the line y equals x. Now, if you can visualize, if you were to fold this piece of paper over that blue line, the black graph would end up right on top of the red graph. That means that they are inverses of one another. So if you ever can reflect a graph over the line y equals x and get another graph, those two graphs are inverses of one another. So make sure you have this note about the line y equals x in your notebooks. In this example, I want to show you that not every function has an inverse function. Because remember, an inverse function, we're reflecting it over that line. So when we reflect it, it may not pass the vertical line test. Okay, so an inverse has to be a function. So here's an example where we have a function. This is a quadratic, so it's a parabola. And I've restricted the domain. So you see here that I'm saying that x has to be greater than or equal to -1. So I'm going to first draw a little sketch of this function, just the entire function. Okay, so this would have its vertex at -1, so this looks like this. Okay, so this is the entire function. Now, if I were to do what we just learned on the previous slide, and if I were to graph the line graph the inverse by reflecting it over the line y equals x. Let me put that on there quickly. Okay, so if I reflect it over this line, then I would get something that looks like this. It would still go through 1, it would go through, 0, -1 instead of -1, 0. And then it would look like this. Okay, and so these two are technically inverses of one another, except that this black graph fails the vertical line test because it is intersecting this vertical line in two places. So this is not a function. And since it's not a function, there is no inverse. Okay, because an inverse has to be a function. That's why I restricted the domain up here. So I'm saying x has to be greater than or equal to -1, and if we go back to my blue graph here, that means if it's greater than or equal to -1, I wouldn't have any of this piece. So I would just have this piece on the right, which means that when I reflect it, I wouldn't have this piece down here. I would just have this piece. And so now it is a function. Okay, so any quadratic or anything like that, will not have an inverse unless you restrict the domain. So I would like you to find the equation for this inverse as I did 2 examples previously. So I've restricted the domain, so it's okay, and we'll talk about how you would have to restrict the domain of the inverse function. But I would like you to, the last thing you need to do here, before the last 2 note slides, is to find the inverse equation for this. So you may want to pause the video until you've completed that. Okay, hopefully you found the inverse function. Our final slide is just a note slide, which wraps up what I just said. An inverse has to be a function. So to see if a function has an inverse, you can use a horizontal line test. You can look back at the last example to see if I had drawn a horizontal line through that original parabola. Okay, so horizontal line. Now we have our vertical line test, right, which says if a graph is a function. The horizontal line test will tell you if you have an inverse function. So because my graph is going through 2 points, when a horizontal line is drawn, that tells me that even though this is a function, okay, so this is fine, there is no inverse function because it fails a horizontal line test. And that should make sense because I'm going to flip it over this line, so it's going to turn out to be sideways each time. I hope this video helped, and we'll do more of these in class tomorrow.